Hey, good afternoon, everyone. My name is Stan Chung. I'm currently a principal research scientist from Hewlett Packard Labs in California. And today I'll be talking about our recent progress on heterogeneous 3-5 silicon non-volatile photonics. So I wanted to first start off with a few motivation slides, and one of them is on the rising demand for compute power. So this graph shows just that. The y-axis shows petaflop days. And before 2012, compute power demand has doubled every 24 months in accordance with Moore's law. Since 2012, with the advent of AlexNet and the use of GPUs for computing, that demand has doubled every 2 months, mainly driven by AI applications like large language models. Um, so essentially, ML compute is outpacing Moore's law, and that doubling rate has been 12x and probably more even recently. So this colored graph over here shows the accuracy of these models versus the operations needed. Essentially, the higher accuracy requires more compute power. So much more compute power that these large language models, it's been estimated that they consume more than 10 to the 6 kilograms of CO2. And just to give reference over here, this is your average human life indicated by the orange bars, car and the train. So here's the slide indicating the arguments for neuromorphic photonic computing. This chart is taken from Mitchell-Namias, indicating that neuromorphic photonics, put my laser on, neuromorphic photonics has the potential to boost computational efficiency for certain computational speeds. The argument is that there's ultra low latency for matrix spectral multiplication and general matrix multiplication in a single clock cycle. There's high energy efficiency. Data movement is at the speed of the light without having a length dependent impedance. And there's really high throughput where analog data is encoded possibly at greater than 50 gigahertz. And there's this inherent parallelism of photonics, meaning you can encode in wavelength, mode, polarization, frequency. So here we see typical digital electronics. Those are done by Google TPUs or NVIDIA chips. And we have some more state-of-the-art neuromorphic electronics based on memristors or flash memory. One of the approaches worth thinking of is using this crossbar array also, but with optical ring resonators with co-integrated memristive or flash memory elements. So for electronic matrix processors, that's shown on the left, they're based on spatial accumulation or this systolic array. And they take a certain number of clock cycles that scale with how large the particular matrices are. For optical matrix processors, shown here, we can perform MBM or general matrix multiplication in a single clock cycle. So one particular and popular architecture is based on a mesh of Mach-Zehnder interferometers, and it's defined by U here. Alternatively, there are micro-ring resonators configured in a crossbar array where particular wavelengths can be processed and weighted, shown here. Over on the right is Envision Optical AI ML accelerator with full CMOS integration with your ADCs and DACs and your off-chip and on-chip memory, as well as your modulator encoders and also lasers. So there's quite a few challenges to realize practical use of optical computing, and we won't get into all the challenges, but one of the issues I wanted to point out is lack of practical memory. So here's Light Matter's optical compute core. We can see that the inputs and outputs, as well as weights, require memory access, which also require DACs and ADCs. So there's this inherent latency and energy bottleneck at the interface between optics and electronics. In fact, this memory issue is known as the von Neumann bottleneck, and people have explored and are exploring currently in-memory computing solutions to alleviate that. Over on the right, we have this really nice system-level study of a photonic AI accelerator. It's kind of very involved. If you look at the upper left-hand side, you'll see that only about 10% of the overall power is consumed by the optical devices. The rest is this die-to-die interconnection, as well as your DACs and ADCs and memory. So people are looking at solutions to perform in-memory computing. In fact, you can do this in-memory computing with a device known as a memristor. And this was theorized by Leon Chua in 1971 to be the fourth passive circuit element. And it's a fundamental element. You have your resistors, capacitors, inductors, and here you have your memristors. This was experimentally demonstrated by Stan Williams and his group by HP Labs in 2008 using a 40 nanometer cube of titanium dioxide. On the lower half, you have this perfect 2-to-1 ratio of oxygen to titanium. And on this upper half, you have 0.5% of the oxygen missing, as well as the titanium in here. So if we apply a positive voltage on the blue electrode, the positive oxygen vacancies are repelled down into the insulating titanium dioxide. This increases the conductivity of the entire switch. Now, conversely, if we apply a negative voltage, that pulls the positively charged oxygen vacancies back up, and this makes the switch more resistive. So what makes the switch non-volatile is that when the voltage is removed, these oxygen vacancies are frozen in space. They don't migrate or diffuse. And then if we perform our IV sweeps back and forth, we see this nice hysteresis curve in the IV indicating that there's non-volatility in the conductance. So this was experimentally demonstrated in 2008. It's 2024. The memristor is nothing new to HP Labs. But as photonics guys, we were unaware that this device was a byproduct of our process, being the heterogeneous 3-5 silicon process, which made things really convenient. And I'll talk about that next. So at HP, we're known for hybrid 3-5 silicon platform, where we wafer bond 3-5 compound materials onto silicon. Over on the left is an energy band diagram for indium phosphide, could be gallium arsenide. It's known as an indirect bandgap material, where this direct overlap of electrons and holes cause efficient recombination of carriers, such that useful optical gain can be achieved. Over on the right is the energy band diagram for silicon, and it's known as the indirect bandgap material. One can see that there's this momentum mismatch between the bands, and it requires a photon for recombination, which is a really inefficient process to generate light. So we wafer bond either indium phosphide or gallium arsenide onto silicon for lasers on silicon. How do we perform this bonding process? We usually start with two pristine materials of 3-5 and silicon on insulator. You can take two avenues. You can do this O2 plasma treatment, or you can do this SiO2 deposition and do a really fine CMP polish. But whatever avenue you take those two and you mate them, and you do thermal compression bonding. And at the end, you do substrate removal after your CMP, and what you're left with is very clean and thin 2-micron thick epitaxial layer of 3-5 on silicon. So in between these bonding materials, we usually have some combination of aluminum oxide or hafnium dioxide shown here. See on the left-hand side, we have our 3-5, right-hand side, we have our silicon. So in order to resistively switch the memristor, an electroforming process creates this interchange of oxygen in a semiconductor atom. It's induced by applying a high enough positive bias voltage across this memristor. So this high electric field breaks some of the aluminum oxide bonds, causing oxygen atoms to migrate towards the semiconductor regions, and that leaves behind negatively ionized vacancies within the aluminum oxide layer. In these oxygen vacancies, they form these localized aluminum-rich channels, and they're known as conductive filaments, and this allows current to flow and effectively increase the conductivity of the oxide material. To reverse this process, we simply apply electric field in the opposite direction, and that causes a sufficient current flow and hence localized Joule heating. And so that ruptures these conductive filaments, which essentially resets the memristor back into the high resistance state. So by alternating the polarity of your electric field, we go into this low resistance state, high resistance state, and onwards. And so if we do that, again, we look at these IV curves. We start at 0 volts. We start in a high resistance state, and by switching it on, we go into a low resistance state. Reversing the polarity, we're at a low resistance state, and go back to a high resistance state. So you get these really nice hysteresis curves indicating memristive behavior on our 3,5 silicon hybrid platform. Here's some SEM pictures that show what this structure looks like. We have this aluminum oxide in between the gallium arsenide and silicon, and we've been able to substantiate these designs onto ring resonators as well as Mach-Zehnder interferometers. So here, in this slide, I'll be talking about some of the device characteristics of that memristive optical ring resonator. Again, we do this IV curve. So we do this electroforming, and then we can set this device and we can reset this device electrically. While doing that simultaneously, we've also tracked the optical response. So our initial state is indicated by this orange curve. That's in a high resistance state. And so we set this electrically, and we look at the optical response. We can see that it switches to a low resistance state, and that's a non-volatile operation. And then we can reset this almost back to the original position, pretty close. And then we can also do this intermediate state indicated by this green curve, and that depends on how we set the current compliance. So we can have non-volatile multi-bit optical states. After setting these devices, we've also looked at the time duration, or how long-lived these devices are. You see on the x-axis we have time, and the shift in this wavelength on the y-axis. Typically these last 12 hours. There's some instability afterwards, which require more research. We've also tracked the resistance over that time, stable up to 12 hours. And then we've also cycled these devices from low resistance state to high resistance state for up to 1,000 cycles shown here. So the executive summary is that set energies require 0.15 picojoules, and then reset energy is 0.36 femtojoules. So here I wanted to make a slide on how people use memristors for in-memory computing. They're configured in a crossbar array, shown in figure A, and essentially allows matrix spectral multiplication in a single step. So the matrix GMN is set by these memristors. Then a 1D voltage array defined by Vn is applied to the rows, and the resulting multiplication is performed in one step and then read off as an array of current. For an optical memristor array, we similarly use a crossbar array, except the intersection points are replaced by these ring resonators, also with embedded optical memristors, the ones we just talked about. And so this allows for multiple wavelengths to be processed for general matrix multiplication. So we've also investigated different types of memristor material stacks based on alternating aluminum oxide and hafnium dioxide layer. This was actually inspired by a paper that showed improved memristor reliability with this particular stack. It's a bit more complicated, but it operates on the principle of filamentation formation. So here's an image of these fabricated devices, and some of our test structures are shown here. And then here we have energy dispersive spectroscopy or EDS line scans to show that we do indeed have alternating layers of aluminum oxide and hafnium dioxide. And then we've also performed IV scans. Here by applying voltage, we see this electroforming or the onset of electroforming, and then we can do these electrical set and resets over multiple cycles. And then we've also looked at atomic mapping, indicating the structure is what it is. And then, yeah, so we look at this for initial state, set state, and reset as well, indicating that the films are intact, that there's no delamination from the wafer bonding. So we've used some of these alternating dielectric memristive stacks in Mach-Zehnder interferometer. Here we see this SEM cross-section of how the mode is guided and its overlap with the memristive region. It's a very low confinement, but it's enough to cause significant index changes in the particular waveguide, and then that translates to pretty large amplitude changes. So over on the left on this graph, we do our IV scan again. We go from a high resistance state, it switches on, and it becomes a low resistance state. And then if we want to reverse this process, we can do this rupturing of the conductive filament by applying a voltage where we go from a low resistance state back to a high resistance state. And so if we look at the resistance versus voltage, the difference between these high resistance and low resistance states is pretty significant, several orders of magnitude, indicating decent memristor performance. So at the same time, while performing these IV scans, we've also looked at the optical spectrum shown on the right-hand side. And I've color-coded these to make these things more understandable. You can see that by going from 0 volts to minus 17 volts to at the onset of filamentation formation, we can get more than a pi phase shift in this Mach-Zehnder. And then when we turn off the voltage, we ramp back down to 0 volts, it essentially stays there. And so we turned off the voltage, anything to the voltage power supply, and it just stays, indicating zero static power consumption for the shift. We've also tried resetting this. So again, these things are color-coded. There's this red shift, and then finally a blue shift. It's not a complete optical reset, but recently we've tested some alternative devices and have gotten better resets. So one of the things we've also looked at is longevity of the photonic memristor and also multi-state operation. Here on the left-hand side, the red curve indicates the initial state at 0 volts. We can set it with a particular set voltage and turn off the voltage. And you can see that there's a certain phase shift associated with it. And we record that data for over 24 hours, so it's very stable. Now we want to see if we can initiate a different state, a different non-volatile state. Indeed, we do that. And we turn off the voltage. And we measure this for 24 hours again. So it's very stable, indicating that we can have long-lived multi-state optical memory states. Over on the right-hand side, it's a little bit involved. But if we just look at the circled data points, I've basically taken the resonant dips for the gray and blue curves and tracked it over 24 hours. So you can see that the wavelength of these dips are quite stable throughout time. Key takeaway is that we can perform phase tuning with near zero static power consumption. We can tune to desired wavelength, and these set states are stable by plus or minus 0.05 nanometers for 24 hours. And you can imagine we can instantiate these optical memrisitors in a whole host of different devices like lasers, resonators, lattice filters. And more recently, we started looking at larger systems like programmable photonic FPGAs and optical matrix multipliers. Next, I wanted to talk about charge trap flash memory. Flash memory is nothing new. It dates back to 1967 by Kang and Z. So in order to program or store information, we apply voltage on the source and drain regions to create this channel of electrons. And the gate voltage is applied to the control gate, which causes the electrons to basically tunnel through and contract in this charge trapping layer, this yellow colored layer. And then to erase that, we apply an opposite bias on the control gate to remove that. And then this can be understood by these energy band diagrams, but maybe we won't go through that here. But we've also been able to incorporate photonic flash memory alongside with our photonics. Here you can see that in this TEM microscope picture. So we use two trapping layers indicated by this turquoise colored region to increase the trapping density. And then these kind of peach colored regions are these tunneling and blocking oxides. But by applying the appropriate voltage through hot injection or electron tunneling, we can inject electrons or even holes into these charge trapping layers. Electrons are trapped and they redistribute the electric field and then attract like positive charges, which causes a change in the refractive index. So characteristic of flash memory is based on this CV curve. Here we've tracked both the CV as well as the optical transmission. So starting from 0 volts and going up to 8 volts, we can see there is this hysteresis in the capacitance, but there's also this very nice hysteresis in the optical transmission. This is for our MZI structure. After programming it with memory, we can erase that memory, and that almost goes back to its initial optical state. And we've been able to do this with multi-states up to 4 states, as shown here. And then we've been able to cycle these for quite reliably. And we've also tested time duration of these states, and they're long-lived for up to 24 hours and most likely beyond. So here is just one example of a device that incorporated this photonic flash memory. We have these doubled coupled ring structures, and these were initially used for bandpass filters. But by setting these rings, we can see that we have this initial resonance for one of the rings. And by applying the appropriate program or write voltage and then turning that voltage off, we can see that there's a shift, a small shift, but enough to cause significant amplitude differences. And then we can erase this, essentially going back to the original position quite well. And then we looked at the endurance of these set operations as well as the reset operations. So it's pretty stable over time. And then we've also been able to incorporate some of these charge trap memories into our 3.5 silicon microring lasers, as shown here. Here we have an array of microring lasers. Have this charge trapping layer of aluminum oxide in between 3.5 and silicon. Over on the right-hand side, these are the various lasing states, both non-volatile and volatile. We start with this initial state and can't really be seen here, but we apply a right voltage, and then that results in a non-volatile shift in the wavelength. And then we can erase this. That's a non-volatile operation. And after a certain time, it resets, it jumps back to the original position. And so by tracking these peak wavelengths, we plot that in this graph here, indicating non-volatile right and reset operation. We've also performed cyclability experiments on these devices, running out of time, but we can go up to 100 cycles. And there's enough shift, well, there's 80 picometer shifts, still small, but that's enough for a 47 dB change in extinction. This is for the left facet, and bottom is for the right facet. We've also performed electro-optical non-volatile writing for this array of lasers. So for each of these lasers, we can obtain 4 non-volatile states for each of these 5 lasers. So we essentially have an optical memory bank here. So in closing, 3.5 silicon heterogeneous platform offers a promising platform for neuromorphic computing. We've demonstrated non-volatile optical memristors co-integrated with 3.5 silicon photonics. Also non-volatile charge trap flash memory with our 3.5 silicon photonics. This can be used for energy efficient and low static power devices for applications other than neuromorphic computing, such as RF photonics, optical switching, phase arrays, et cetera, et cetera. And so one of the things we want to emphasize is breaking a von Neumann bottleneck on an integrated photonic platform. So if anyone's interested, feel free to contact me. My contact information is here, and that concludes my talk. Thank you.